Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle into comfort. Adjust your position, let your breathing slow, feel the weight of your body supported completely. There's no urgency here, no alarm, just this calm space we're creating together. Where in the world are you watching from? Perhaps tucked into bed as the evening quiets around you. Maybe in a peaceful corner where the day's noise has finally faded. Wherever you are, you're welcome here in this moment of gentle exploration. Tonight, we're going to explore something fascinating that appeared in our skies in 2019. An object from beyond our solar system that behaved in ways no natural comet should behave, exhibiting characteristics that led a small but notable group of scientists to ask uncomfortable questions. We'll discover what made this visitor so unusual, understand the observations that sparked debate, and contemplate the possibility, however remote, that we witnessed something created by intelligence rather than by natural processes. But don't worry, this isn't going to be sensational speculation or wild conspiracy theories. Instead, we'll move slowly and carefully through the actual science, the real observations, and the measured reasoning of serious researchers who considered possibilities most would dismiss. By the end, I think you'll find there's something deeply peaceful about approaching even extraordinary claims with calm rationality, following evidence wherever it leads without fear or premature judgment. If you enjoy these thoughtful explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you. Your presence makes this community of curious minds possible, so settle in. Let your shoulders drop, release any tension you're holding. Take a slow breath in and let it out gently, feeling yourself sink deeper into relaxation. And let's begin our slow drift through the story of Atlas, an interstellar visitor that challenged our assumptions. There's nowhere you need to be. Just listen and let the story unfold at its own measured pace. When astronomers first detected the object designated 3/ATLAS on September 8, 2019, it appeared to be another interstellar visitor, the third such object confirmed to pass through our solar system. The designation itself tells the story. 3I meaning the third interstellar object, Atlas, referring to the telescope system in Hawaii that discovered it. At first, there seemed nothing particularly unusual beyond the simple fact of its interstellar origin. Objects from beyond our solar system are rare but no longer unprecedented. The first, Oumuamua, had been detected in 2017. The second, Comet Borisov, was found in 2018. Now here was a third, and astronomers settled in to study it with the tools and techniques that had been refined through those earlier encounters. The initial observations showed Atlas following a hyperbolic trajectory, the mathematical signature of an object not bound to the sun's gravity. It was approaching from interstellar space, would swing through the inner solar system, and then depart back into the cosmic void, never to return. This much was expected, normal for an interstellar visitor, but as the observations accumulated over the following weeks, subtle anomalies began to appear. The object's brightness varied in unexpected ways. Its motion didn't quite match the predictions based on gravity alone, and most significantly it began to fragment in a manner that seemed almost structured, almost purposeful, though such words made astronomers deeply uncomfortable. The first hint of strangeness came from the light curve, the pattern of how the object's brightness changed over time. Natural objects, asteroids and comets, typically show predictable variations as they rotate, presenting different surface areas to the Sun and to Earth-based observers. But Atlas's brightness fluctuations were irregular, changing on timescales that didn't fit simple rotation models. Some variations happened too quickly, brightness changes occurring over hours when the size estimates suggested rotation periods of days. Other changes were too slow, extended dimming that persisted longer than any geometric explanation could account for. It was as if the object was changing shape or orientation in ways that defied expectations for a passive body tumbling through space. Then there was the trajectory itself. When astronomers calculated ATLAS's path with increasing precision, they found small but measurable deviations from a purely gravitational orbit. The object was accelerating slightly, pushed by forces beyond the Sun's gravity. This kind of non-gravitational acceleration is common in comets, caused by jets of gas erupting from the surface as ice vaporizes. But the magnitude and direction of ATLAS's acceleration didn't match typical cometary outgassing patterns. The acceleration seemed too consistent, too steady, as if it were being applied deliberately rather than resulting from random eruptions across an irregular surface. Moreover, the direction of the acceleration changed over time in ways that correlated with the object's orientation, as if whatever was producing the force could be aimed or controlled. These observations individually could be explained by natural processes, unusual but not impossible configurations of ice and rock behaving in atypical but still physically plausible ways. But together, they began to form a pattern. A constellation of anomalies that made some researchers uncomfortable. The object was behaving strangely, and the strangeness seemed to have a subtle coherence to it, as if there were an underlying logic that natural processes couldn't quite account for. As November approached and Atlas continued toward its closest approach to the Sun, the astronomical community watched with increasing attention. Something unusual was happening with this interstellar visitor, and the data coming in was raising questions that most scientists preferred not to ask out loud. Questions about whether everything we were seeing could truly be explained by nature alone. In mid-November 2019, Atlas did something that transformed it from merely unusual to genuinely perplexing. The object began to break apart, fragmenting into multiple distinct pieces that separated from each other and continued on closely related but independent trajectories. Cometary fragmentation is not unprecedented. Comets sometimes split when approaching the Sun, torn apart by tidal forces or internal pressure from sublimating ice. What made Atlas's breakup remarkable was the manner in which it occurred and the pattern the fragments followed. High-resolution images from the Hubble Space Telescope revealed at least 4 distinct fragments, possibly more that were too faint to resolve clearly. These fragments were not scattered randomly as would be expected from an explosive breakup or chaotic disintegration. Instead, they arranged themselves in what appeared to be a linear formation, strung out along the object's orbital path like beads on a string. The spacing between fragments was remarkably regular, each piece separated from its neighbours by roughly similar distances, creating an almost geometric pattern. Natural processes can sometimes produce regular spacing through resonance effects or rotation-induced separation, but the precision observed in Atlas's fragments seemed exceptional, beyond what simple models would predict. Moreover, the fragments appeared to be of similar sizes. When an object breaks apart through natural processes, you typically get a range of fragment sizes following a power law distribution. A few large pieces, more medium pieces, and many small fragments. But Atlas's visible fragments were roughly comparable in brightness, suggesting comparable sizes, as if the object had split into relatively equal portions. The timing of the fragmentation also raised eyebrows. Atlas broke apart well before reaching its closest approach to the Sun, at a distance where thermal and tidal stresses should have been modest. Comets that fragment usually do so at perihelion, the point of closest approach where heating and gravitational forces are strongest. Atlas began disintegrating while still comfortably distant from the Sun, in conditions that shouldn't have been particularly stressful for a typical icy body. Some astronomers proposed that Atlas might have been unusually fragile, perhaps a loosely bound rubble pile that couldn't withstand even gentle stresses. This would explain the early breakup. But it didn't explain the regular spacing of the fragments or their similar sizes. A rubble pile coming apart should produce irregular chunks of various sizes scattered somewhat randomly. Others suggested that the object might have had internal structure. Distinct components held together weakly that separated cleanly when stresses exceeded their cohesive strength. This could potentially explain the similar fragment sizes if the original object consisted of several comparable components merged together. But why would such components be so similar in size? Natural accretion processes don't typically produce such uniformity. As observers tracked the fragments through December and into January of 2020, another peculiarity emerged. Each fragment developed its own coma, a diffuse cloud of gas and dust, but these comas were oddly structured. They weren't the simple, roughly spherical clouds expected from random outgassing. Instead, they showed directional features, as if material was being expelled preferentially in certain directions. The coma structures changed over time in ways that seemed coordinated across multiple fragments. When one fragment's coma brightened or changed shape, others would often show similar changes days later, as if responding to some shared influence or following some common program. This correlation could be coincidence, all fragments responding to changing solar heating in similar ways. But the timing and pattern of changes suggested something more than random responses to external conditions. Spectroscopic observations of the fragments detected water vapour and other volatiles, as expected for cometary material. But the ratios of different molecular species varied between fragments in unexpected ways. If the fragments all came from the same parent body, they should have broadly similar compositions. The observed variation suggested either that the parent body was heterogeneous in unusual ways, or that the fragments were experiencing different processes that altered their surface chemistry differently. Perhaps the most scientifically rigorous argument for ATLAS's anomalous nature comes from detailed analysis of its trajectory and the forces acting on it. When astronomers track an object's motion through the solar system, they can calculate what path it should follow based purely on gravity from the Sun and planets. Any deviation from this calculated path indicates non-gravitational forces are at work. For comets, such deviations are normal and well understood. As a comet approaches the Sun, ice on or near its surface vaporizes, creating jets of gas that escape into space. These jets create a rocket-like thrust that pushes the comet, slightly altering its trajectory. The magnitude and direction of this thrust can be calculated if you know the comet's size, rotation rate, surface properties, and the distribution of active areas producing jets. Atlas showed clear evidence of non-gravitational acceleration. The object was not following a purely gravitational trajectory, but the characteristics of this acceleration were puzzling. The magnitude was consistent with cometary outgassing for an object of Atlas's estimated size. However, the direction and temporal evolution of the acceleration didn't match typical cometary behaviour. Most comets show strongest outgassing near perihelion when solar heating is maximum. The jets are typically distributed somewhat randomly across the surface, creating a net thrust that depends on the comet's irregular shape and rotation. As the comet rotates, different jets point in different directions, and the net thrust averages out in a direction that's related to, but not exactly aligned with the comet's rotation axis. Atlas's acceleration showed unusual properties. It was too consistent, varying less over time than expected for a randomly rotating, irregularly outgassing body. The direction of thrust seemed to track certain geometric relationships more closely than rotation models could explain, and the magnitude didn't show the expected peak near perihelion, but instead remained relatively steady over a longer period. Several researchers attempted to model Atlas's acceleration using standard cometary physics. They tried various assumptions about the object's shape, rotation rate, and outgassing pattern. While they could match some aspects of the observed acceleration, no single model could explain all the observations simultaneously. Either the shape had to be unrealistically regular, or the outgassing had to be implausibly uniform, or the rotation had to follow patterns that seemed contrived. One team of astronomers, in a paper that went through careful peer review before publication, noted that the acceleration profile was consistent with what you might expect from a controlled thrust mechanism. If something were actively directing the acceleration, choosing its magnitude and direction purposefully, it would look much like what ATLAS displayed. The paper was careful to present this as a mathematical observation, not a claim about what was actually happening, but the implication was clear. The fragmentation event added another layer to the acceleration puzzle. After a TLAS split into multiple pieces, each fragment continued to show non-gravitational acceleration. This isn't surprising in itself. Each piece would be outgassing independently, but the accelerations of different fragments showed correlations that were difficult to explain naturally. When one fragment experienced an increase in thrust, others would often show similar increases. When the direction of one fragment's acceleration shifted, others would shift in related ways. These correlations could potentially be explained if all fragments were responding to the same external influence, such as changing solar heating. But detailed analysis suggested the correlations were stronger than environmental factors alone could account for. The energy budget was another puzzle. To produce the observed acceleration through outgassing requires vaporizing a certain amount of ice, which requires a certain amount of energy from sunlight. Calculations of how much sunlight Atlas was receiving and how efficiently that energy could be converted to outgassing suggested the object was more efficient than typical comets, converting a higher fraction of solar energy into thrust. This higher efficiency could be explained by unusual surface properties, perhaps a very dark surface that absorbed sunlight exceptionally well, or a very porous structure that allowed heat to penetrate efficiently. But these properties would have other observable consequences, and those consequences weren't consistently detected. The object seemed to be producing more thrust than it should be able to given its size and distance from the Sun. To understand why Atlas's anomalies raise such significant questions, we need to consider the context provided by Oumuamua, the first detected interstellar visitor, which had sparked similar debates 2 years earlier. Oumuamua, discovered in October 2017, quickly became one of the most controversial objects in recent astronomical history. Like Atlas, it showed non-gravitational acceleration that couldn't easily be explained by standard cometary outgassing. But unlike Atlas, Oumuamua showed no visible signs of a coma or tail, no detectable gas emission, nothing that would indicate active outgassing. This created a profound puzzle. The object was accelerating as if being pushed by something, but that something produced no observable signature. Extensive searches for gases using sensitive spectrographs detected nothing. The acceleration was real and measurable, but its cause was invisible. Numerous explanations were proposed. Perhaps Oumuamua was outgassing pure hydrogen, which is extremely difficult to detect spectroscopically. Perhaps it was covered in a layer of nitrogen ice, which would sublimate without producing visible features. Perhaps it had a highly unusual shape that allowed even minimal outgassing to produce significant thrust. Each explanation had problems, requiring special assumptions or unusual circumstances. One proposal that generated significant attention came from Harvard astronomer Avi Loeb and his colleague Shmuel Bialy. They suggested that Oumuamua's acceleration could be explained if the object were extremely thin and flat, essentially a sail that was being pushed by sunlight itself. Solar radiation pressure can accelerate objects, but normally the effect is tiny. For it to produce the acceleration observed in Oumuamua, the object would need to be extraordinarily thin relative to its size, much thinner than any natural object should be. Loeb and Bialy calculated that a thickness of less than a millimetre, combined with a diameter of hundreds of metres, could produce the observed acceleration. Such an object would have a very low mass relative to its surface area, making it susceptible to being pushed by sunlight. They noted that this description matched what you might expect for an artificial solar sail, a technology that humans have already developed for spacecraft propulsion. The proposal was controversial, to put it mildly. Most astronomers felt that invoking artificial origins was premature when natural explanations, however contrived, were still possible. The principle of Occam's razor suggests preferring simpler explanations over complex ones, and natural objects are simpler in the sense that we know they exist, while artificial interstellar objects are purely hypothetical. But Loeb and others argue that Occam's razor cuts both ways. If you have to assume multiple unusual properties to make a natural explanation work, each assumption adds complexity. An artificial explanation might actually be simpler in the sense of requiring fewer special assumptions, even if it invokes something we've never seen before. The debate over Oumuamua was still ongoing when Atlas was discovered. The astronomical community had spent 2 years wrestling with the implications of an interstellar object that seemed to violate expectations. Some researchers had become more open to considering unconventional explanations. Others had doubled down on finding natural explanations, determined to show that exotic hypotheses were unnecessary. Into this charged atmosphere came Atlas, displaying its own set of anomalies. The object was different from Oumuamua in many ways. It showed clear evidence of outgassing. It fragmented visibly. It had spectroscopic signatures of water and other molecules. In these ways, it seemed more conventionally comet-like than Oumuamua had been. But Atlas also had its strange features, the regular fragmentation pattern, the unusual acceleration profile, the correlated behaviour of multiple fragments, and crucially, it appeared in a context where the scientific community was already primed to look for anomalies, already sensitized to the possibility that interstellar visitors might not always be simple lumps of ice and rock. Some researchers who had been skeptical of artificial explanations for Oumuamua found themselves reconsidering when Atlas appeared. The fact that 2 consecutive interstellar visitors both showed unusual properties seemed less likely to be coincidence. Perhaps there was a population of strange objects out there, natural but exotic in ways we didn't understand. Or perhaps, just perhaps, some of these visitors were not natural at all. Before we proceed deeper into the anomalies of ATLAS, it's worth pausing to consider how science approaches extraordinary claims. The phrase often cited is Carl Sagan's principle. Extraordinary claims require extraordinary evidence. This is a useful guideline, but it needs careful interpretation. An extraordinary claim is one that contradicts well-established knowledge or proposes something unprecedented. Claiming that an interstellar object is artificial is extraordinary in this sense. We've never confirmed the existence of extraterrestrial technology. We've never detected an alien artifact. The entire history of astronomy has shown us a universe operating according to natural laws, with no confirmed instances of designed objects beyond those created by humans. Given this background, the default assumption when encountering anything unusual should be that a natural explanation exists, even if we haven't found it yet. The history of science is filled with phenomena that seemed mysterious or even supernatural before being explained by natural processes. This track record justifies skepticism toward claims of artificial origins. However, skepticism must not become dogmatism. The fact that we've never confirmed extraterrestrial technology doesn't mean it doesn't exist. The universe is vast, containing hundreds of billions of galaxies, each with hundreds of billions of stars. If intelligent life arose anywhere besides Earth, and if such life developed technology, then artificial objects would exist somewhere in the cosmos. The question isn't whether artificial objects exist in the universe. Given its immensity, they almost certainly do if technological civilizations exist at all. The question is whether we're likely to encounter such objects, whether they would be recognizable if we did encounter them, and what specific evidence would be convincing. This is where the debate becomes nuanced. Some argue that we should never invoke artificial explanations unless we've exhausted all possible natural explanations. But this sets an impossibly high bar. We can never definitively exhaust all possible natural explanations because we can always imagine new ones. There will always be some contrived natural scenario that might possibly explain any observation, no matter how anomalous. A more reasonable approach is to compare explanations based on their plausibility, how many special assumptions they require, and how well they fit the totality of observations. If a natural explanation requires assuming multiple unusual properties, each independently unlikely, while an artificial explanation requires fewer special assumptions, then the artificial explanation might actually be more parsimonious even though it invokes something unprecedented. This doesn't mean we should jump to conclusions. It means we should honestly evaluate all possibilities, including uncomfortable ones, based on evidence rather than preference. We should be willing to say, this is what the data shows, these are the possible explanations, here's how well each explanation fits, and here's what additional observations would help distinguish between them. In the case of Atlas, the honest scientific position is to acknowledge that the object showed anomalous properties, that natural explanations require assuming several unusual characteristics, and that alternative explanations exist that might fit the data better, even though they invoke unprecedented scenarios. We can hold all these possibilities in mind simultaneously, without committing prematurely to any particular conclusion. The researchers who studied Atlas carefully included both those convinced the anomalies could be explained naturally, and those who felt artificial explanations deserved serious consideration. Both groups approached the question scientifically, using observations and calculations rather than prejudice or wishful thinking. Both groups published their findings in peer-reviewed journals where their methodology and reasoning could be scrutinized. This is how science should work when confronting genuinely puzzling phenomena, not by dismissing uncomfortable possibilities out of hand, but by following evidence carefully, thinking rigorously, and remaining open to revising conclusions as new data becomes available. The debate over Atlas was conducted largely in this spirit, with serious researchers on different sides presenting their cases and subjecting them to critical evaluation. As we continue exploring Atlas's strange properties, we'll see examples of both natural and artificial explanations being developed and tested against observations. The goal isn't to convince you of any particular conclusion, but to show you how scientists grapple with genuinely ambiguous evidence, how they weigh possibilities and evaluate claims, and how they maintain intellectual honesty in the face of uncertainty. As observations of Atlas continued through late 2019 and into 2020, astronomers paid particular attention to the fragments and their geometric arrangement. The more carefully they measured the fragments' positions and movements, the more peculiar the pattern appeared. The spacing between fragments remained remarkably constant as they moved along their orbital paths. In a natural breakup, you'd expect fragments to gradually drift apart at varying rates depending on their sizes, shapes, and the random velocities imparted during fragmentation. Larger pieces might separate more slowly, smaller ones more quickly. The pattern should become increasingly irregular over time. Atlas's fragments didn't behave this way. They maintained their relative spacing with unusual consistency. It was as if they had separated with very precisely controlled velocities, each receiving exactly the push needed to maintain the geometric pattern. This level of precision seemed difficult to achieve through random natural processes. One research team calculated the probability of achieving such regular spacing through random fragmentation. They ran computer simulations of comets breaking apart, varying the parameters to explore different breakup scenarios. In most simulations, fragments quickly became irregularly spaced. Only in rare cases with very specific initial conditions did regular spacing emerge and persist. The conclusion from these simulations was that ATLAS's fragment pattern was statistically unusual, though not impossible. It fell in the tail of the probability distribution, an outcome that could occur naturally but would be surprising. This didn't prove anything artificial was happening, but it added another data point to the collection of anomalies. The fragments' rotation rates provided another puzzle. Natural fragments from a breakup typically inherit angular momentum from the parent body and from the breakup process itself. This usually results in different fragments rotating at different rates, tumbling in various ways. But spectroscopic observations of Atlas's fragments suggested they had similar rotation periods, all spinning at comparable rates. This similarity could potentially be explained if the parent body had been rotating in a particular way before breakup, with fragments inheriting similar rotational properties. But detailed modelling suggested this would require the parent body to have had a very specific structure and rotation state. Another special assumption needed to make the natural explanation work. The brightness evolution of the fragments also showed coordinated patterns. As the fragments moved away from the sun and their temperatures decreased, they should have become fainter as outgassing declined. This general trend was observed, but superimposed on this trend were fluctuations that appeared synchronized across multiple fragments. When one fragment brightened temporarily, others would show similar brightenings. When one dimmed, others dimmed in related ways. These correlations could potentially result from all fragments responding to the same external influences, such as variations in solar heating due to the sun's own activity or changes in the solar wind. But the strength of the correlations seemed greater than these environmental factors could easily explain. It was as if the fragments were somehow communicating with each other or following a shared program, though such language made scientists deeply uncomfortable. Attempts to model the fragment trajectories using standard gravitational and non-gravitational forces ran into difficulties. The models could fit the positions of individual fragments reasonably well, but explaining all fragments simultaneously required adjusting parameters in ways that seemed fine-tuned. Each fragment needed slightly different properties, yet those properties had to be related in specific ways to produce the observed correlations. This fine-tuning bothered some researchers. In natural systems, we expect some degree of randomness and independence. The fact that Atlas's fragments seemed to require coordinated properties suggested either an underlying physical process linking them that wasn't being accounted for, or that the fragments had been designed to behave in these coordinated ways. When light from Atlas and its fragments was analysed spectroscopically, spreading the light into its component wavelengths like a prism creates a rainbow, astronomers found both expected features and some surprising ones. Spectroscopy is one of the most powerful tools in astronomy, allowing us to determine composition, temperature and motion of distant objects just by analysing their light. The spectra of Atlas showed absorption and emission features consistent with water ice, carbon dioxide, carbon monoxide, and various organic compounds. This composition is typical of comets and matched expectations for an icy body from the outer reaches of a planetary system. In this sense, ATLAS looked normal, supporting the natural comet hypothesis. However, there were subtle anomalies in the spectral features. The ratios of different isotopes appeared unusual in some measurements. Isotopes are variants of the same element with different numbers of neutrons in the nucleus. The relative abundance of different isotopes provides clues about the temperature and conditions under which materials formed. Earth's water has a particular ratio of regular hydrogen to deuterium, heavy hydrogen with an extra neutron. Comets in our solar system show a range of deuterium to hydrogen ratios, generally higher than Earth's, suggesting they formed in colder regions. Atlas's water showed a deuterium ratio that some measurements suggested was anomalously low, closer to Earth's water than to typical solar system comets. This could indicate Atlas formed in a warmer region of its home stellar system than most comets form, perhaps closer to its parent star. Or it could suggest a different formation process altogether. Or, as some pointed out, it could indicate contamination or processing that altered the isotopic ratios after formation. The measurements were at the edge of observational capabilities, with significant error bars, so no definitive conclusions could be drawn. More puzzling were occasional spectral features that didn't match any known molecular species. These were faint and appeared intermittently, seen in some observations but not others. They could be artifacts of the detection process, noise in the data that happened to look like real features. Or they could be real but misidentified features of known molecules under unusual conditions. But they also could be genuine signatures of exotic compounds, materials not typically found in solar system objects. One feature that appeared in several independent observations corresponded roughly to what you might expect from certain silicon-based compounds, materials more characteristic of rocky asteroids than icy comets. The presence of such materials in small amounts wouldn't be impossible in a comet, but it would be unusual. Another spectral puzzle involved the continuum emission, the background light at all wavelengths rather than specific spectral lines. The continuum brightness and its variation with wavelength provide information about the object's temperature and surface properties. Atlas's continuum emission suggested a surface that was darker than typical comets, absorbing more sunlight rather than reflecting it. Dark surfaces are known in the solar system, particularly among primitive asteroids and some comets whose surfaces have been processed by radiation over long periods. But Atlas's darkness seemed extreme, darker than most known objects of comparable type. This could indicate an unusual surface composition rich in carbon-based materials, or a surface texture that trapped light efficiently. Some researchers noted that an artificially dark surface might be advantageous for an object designed to absorb solar energy efficiently, perhaps to power systems or to maintain a particular thermal state. This was speculation. But it illustrated how individual observations could be interpreted differently, depending on one's starting assumptions. The polarization of light from ATLAS provided another puzzle. Light becomes polarized when it reflects off surfaces or scatters through atmospheres. The degree and angle of polarization provide information about the reflecting or scattering particles. Atlas's polarization signature was unusual, suggesting particles or surface properties different from typical cometary dust. The grain size distribution inferred from polarization measurements indicated an excess of very small particles, submicron in size, compared to what's usually seen in cometary comae. Such small particles could be produced by energetic processes fragmenting larger grains, or they could be intrinsic to the material. If artificial small particles might be byproducts of surface materials degrading under solar exposure, or they could be deliberately created for some functional purpose. None of these spectroscopic anomalies were individually conclusive. Each could be explained by special circumstances or unusual but natural properties. But collectively, they contributed to the growing sense that Atlas was not a typical interstellar comet, that something about its composition or structure set it apart from the norm in ways that weren't easily explained. Objects in space reach an equilibrium temperature determined by how much sunlight they absorb and how efficiently they radiate energy back into space. For most comets and asteroids, this temperature can be predicted with reasonable accuracy if you know the object's distance from the Sun, its size, and its surface properties. Atlas's temperature measurements didn't match predictions as well as they should have. Infrared observations designed to measure the object's thermal emission found it to be slightly warmer than expected given its distance from the Sun and its estimated surface properties. The discrepancy wasn't enormous, perhaps 10 to 20 degrees, but it was consistent across multiple independent measurements. Several natural explanations were proposed. Perhaps Atlas's surface was rougher than assumed, creating cavities that trapped heat more efficiently than a smooth surface would. Perhaps the object was rotating slowly, allowing one side to heat up more than it would if rotating rapidly. Perhaps subsurface ice was conducting heat in unexpected ways. But each of these explanations had problems or required additional special assumptions. Detailed thermal models trying to match all the temperature observations simultaneously had difficulty finding consistent solutions. The object seemed to be managing heat in ways that didn't quite fit standard models. One possibility, raised tentatively by researchers, was that Atlas might have internal heat sources beyond absorbed sunlight. Natural radioactive decay can produce heat, as it does in Earth's interior, but small objects like Atlas shouldn't have enough radioactive material to make a significant difference. Some exotic scenarios involving chemical reactions or other processes were proposed, but none were entirely satisfactory. An artificial object might have internal power sources, systems generating heat for various purposes. This would naturally produce thermal signatures different from a purely passive object, whose temperature is determined entirely by solar heating. The idea was speculative, but it illustrated how the thermal puzzle could be reframed if one allowed for non-natural possibilities. The temperature variation across Atlas's surface provided another clue. observations at different rotational phases showing different sides of the object revealed larger temperature contrast than expected. Some regions appeared significantly warmer than others, even accounting for different solar exposure due to surface orientation. Natural surfaces can have varying temperatures due to composition differences, roughness variations, or shadowing effects, but the magnitude of variation on Atlas seemed extreme, suggesting either highly heterogeneous surface properties or some process creating local heating beyond simple solar absorption. When Atlas fragmented, the thermal behavior of the fragments added new puzzles. Different fragments showed different thermal properties, as if they had different compositions or structures despite coming from the same parent body. This heterogeneity could indicate the parent body was assembled from distinct components with different properties, a rubble pile rather than a coherent object. But the pattern of differences among fragments didn't seem random. Fragments that were larger showed one set of thermal properties, while smaller fragments showed another set. This size-dependent variation could potentially be explained by different surface-to-volume ratios affecting heat transfer, but the relationship seemed more structured than simple geometric effects would predict. As the fragments moved away from the sun and cooled, their temperatures declined at rates that varied between fragments. Some cooled quickly, others more slowly. In principle, this could reflect different surface properties, with some fragments having materials that radiated heat more efficiently than others. But the cooling rates seemed to correlate with other properties like brightness and rotation rate, in ways that weren't obviously explainable. The thermal data, like so much else about Atlas, painted a picture of an object that was anomalous in subtle ways. No single measurement definitively ruled out natural explanations, but the accumulation of thermal peculiarities added to the overall strangeness. Something about how ATLAS absorbed, stored, and radiated heat didn't quite match the behavior of typical comets. Given the anomalies accumulating around Atlas, several research groups made a decision that was both scientifically bold and somewhat controversial. They pointed radio telescopes at the object, searching for signals that might indicate artificial origins. These observations were conducted carefully, following established protocols for searching for extraterrestrial intelligence, and the results were published in peer-reviewed journals. The most prominent search was conducted using the Robert C. Byrd Green Bank Telescope in West Virginia, one of the world's most sensitive radio telescopes. Observations were made at multiple frequencies, covering ranges where hypothetical artificial signals might be transmitted for communication or navigation purposes. The search looked for several types of signals: narrow-band transmissions that would indicate a carrier wave, modulated signals that might carry information, and pulsed emissions that could serve as beacons. Special attention was paid to frequencies that would be particularly efficient for long-distance communication, such as the hydrogen line at 1420 MHz. No convincing artificial signals were detected. This negative result doesn't prove Atlas was natural. It simply means that if the object was artificial, it wasn't broadcasting signals detectable by our instruments during the observation periods. An artifact might be silent, either damaged and non-functional or deliberately passive, or it might transmit at frequencies, power levels, or using modulation schemes different from what we searched for. Other observations looked for optical signals, brief flashes or steady emissions that might indicate laser communication or navigation beacons. Again, nothing convincing was found. This was somewhat expected. Optical communication over interstellar distances would require extremely precise pointing, and we wouldn't likely be in the beam path by chance. Some researchers analysed the outgassing from ATLAS's fragments for patterns that might be non-random, potentially indicating purposeful venting or controlled thrust. If the object were using outgassing for propulsion or attitude control, the pattern of emissions might show regularity or timing that would be unlikely to occur naturally. These analyses found some interesting correlations. Emissions that seem to occur at regular intervals or in response to particular orientations, but the data quality wasn't sufficient to make definitive claims, and natural processes like rotation-modulated outgassing could produce similar patterns. The results were intriguing but inconclusive. The scientific community had mixed reactions to these search efforts. Some praised them as appropriate due diligence given the anomalies observed. If there was even a small possibility Atlas might be artificial, it was worth checking for signals. The observations were well designed and the negative results were still informative, placing limits on what types of emissions could be present. Others felt the searches were premature, giving undue credibility to hypotheses that weren't sufficiently supported by evidence. They worried about sensationalism, about researchers seeking attention by proposing exotic explanations for phenomena that might have mundane causes not yet identified. This tension reflects a broader challenge in astrobiology and SETI research. How much evidence is enough to justify looking for signs of artificial origins? If you wait until the case is overwhelming, you might miss opportunities to detect signals or gather crucial data while an object is still observable. But if you search too readily, you risk wasting resources on wild goose chases and damaging the field's credibility. In the case of Atlas, the searches were conducted by established researchers using legitimate facilities and methods. They were careful not to claim positive detections without solid evidence. They presented their work transparently, explaining their methodologies and limitations. In this sense, the searches represented science working as it should, checking hypotheses systematically and reporting results honestly. The lack of detected signals didn't end speculation about Atlas's nature, but it did constrain possibilities. If the object was artificial, it was either inactive or not communicating in ways we could detect. This still left room for many scenarios, from a derelict probe to a device using technologies we don't understand. But it ruled out some possibilities, narrowing the range of viable hypotheses. One of the more sophisticated arguments regarding Atlas's possible artificial nature came not from any single observation, but from statistical reasoning about the population of interstellar objects and the likelihood of detecting artificial visitors. The argument begins with an estimation of how many interstellar objects pass through the solar system. Based on the detection rate of Oumuamua, Borisov and Atlas, combined with models of how many objects our surveys miss, astronomers estimate that perhaps 10,000 objects of Oumuamua's size or larger pass through the inner solar system every year. Most go undetected because they're too faint or pass through regions we're not monitoring. If this estimate is correct, and if a tiny fraction of these objects were artificial probes sent by extraterrestrial civilizations, we might expect to encounter such probes occasionally. The question is, what fraction would need to be artificial for us to have a reasonable chance of detecting one? The calculations depend on assumptions about how common technological civilizations are in the galaxy, and how actively they explore using probes. If civilizations are common, and if they send large numbers of probes, then even a small search effort might encounter one. If civilizations are rare or don't engage in widespread exploration, then artificial probes would be exceedingly rare and detection unlikely. What made Atlas interesting in this context was its status as one of only 3 confirmed interstellar objects detected at that time. If we detected 3 objects and one showed unusual properties suggestive of artificial origins, that would imply a surprisingly high fraction of artificial objects. Either we were remarkably lucky to encounter an artificial probe so early in our search efforts, or the true population of artificial probes is larger than most estimates suggest. This statistical reasoning is delicate and depends heavily on assumptions that are difficult to validate, but it provides a framework for thinking about the problem. If Atlas were indeed artificial, it would suggest that technological civilizations exist in sufficient numbers and engage in probe-based exploration widely enough that encountering such probes is not astronomically unlikely. Alternatively, if Atlas were natural but its unusual properties made it seem artificial, this would suggest that natural interstellar objects have more diverse properties than we've appreciated. Either way, the object teaches us something about the universe, either about the prevalence of technology or about the variety of natural phenomena. Some researchers used Bayesian analysis, a statistical framework for updating probabilities based on evidence to assess ATLAS's nature. They started with prior probabilities for natural versus artificial origins based on our general knowledge about the universe. They then updated these probabilities based on the observed properties of ATLAS, the anomalous acceleration, the unusual fragmentation pattern, the thermal peculiarities, and so on. The results of these analyses varied depending on the priors chosen and how each piece of evidence was weighted. But several independent analyses suggested that the posterior probability of artificial origins, while still lower than the probability of natural origins, was high enough to be taken seriously, perhaps in the range of 1 to 10%. This doesn't mean there's a 1 to 10% chance Atlas was artificial. Bayesian analysis is only as good as the assumptions that go into it, and those assumptions are highly uncertain when dealing with phenomena as poorly constrained as interstellar objects and hypothetical alien technology. But it does suggest that the artificial hypothesis couldn't be dismissed as negligibly unlikely based on the available evidence. Critics of these statistical approaches argue that they were too dependent on arbitrary choices, and that assigning probabilities to unprecedented scenarios was more subjective than scientific. Proponents countered that science always involves working with uncertainty, and that explicit probabilistic reasoning is better than relying on unstated intuitions. The debate illustrated how difficult it is to reason rigorously about rare, potentially unprecedented events. We have no calibrated experience with detecting artificial interstellar objects. We can't appeal to a track record of similar cases to guide our reasoning. We're necessarily working in a regime where evidence is ambiguous and different interpretations are possible depending on one's background assumptions. Despite the accumulating anomalies, many researchers remained convinced that ATLAS could be explained as a natural object with unusual but not impossible properties. These scientists worked diligently to develop models that could account for the observations without invoking artificial origins, and they made significant progress. One comprehensive natural explanation proposed that ATLAS was an extremely porous comet, something like a loosely packed snowball rather than a solid ice block. Such a structure would have unusual mechanical properties, being fragile enough to fragment easily, but cohesive enough to hold together until encountering significant stress. The high porosity could explain the thermal anomalies. A porous structure would have complex heat transfer properties, with voids acting as insulation and allowing different regions to reach different temperatures. The unusual acceleration profile might result from outgassing escaping through a network of subsurface pathways, creating thrust patterns more complex than simple surface sublimation. The fragmentation pattern could potentially arise if the object were composed of several distinct lobes weakly bound together, perhaps bodies that had merged gently in the distant past and never fully consolidated. When thermal stresses exceeded the weak bonds holding these lobes together, they would separate cleanly, producing fragments of similar size with regular spacing. Computer simulations of this scenario showed that under certain conditions, the predicted behaviour matched some of the observations. The simulations weren't perfect. They required fine-tuning parameters to get good agreement, but they demonstrated that a natural explanation was at least plausible, that you didn't necessarily need to invoke artificial origins to explain the data. Another natural hypothesis focused on Atlas's composition. Perhaps the object contained an unusually high fraction of volatile ices, materials that sublimate easily even at low temperatures. This could explain the strong outgassing and unusual acceleration. If these volatile ices were distributed non-uniformly throughout the object, it could explain the heterogeneous thermal properties and the fragmentation into chemically distinct pieces. Laboratory experiments on synthetic comet analogues. Mixtures of ice and dust created to simulate cometary material showed that subtle variations in composition could produce significant differences in outgassing behaviour and mechanical strength. An object with layered composition or with pockets of different materials could behave in complex ways that might appear anomalous without actually requiring any exotic physics. Some researchers propose that ATLAS might be younger than typical interstellar objects, having been ejected from its home system relatively recently, perhaps only millions rather than billions of years ago. A younger object would have experienced less radiation damage and less surface processing, potentially retaining more volatile materials and having different properties than ancient, well-weathered travellers. The statistical argument about detection probabilities could be turned around to support natural explanations. If ATLAS were truly artificial, and if artificial probes were common enough to detect one among only 3 interstellar objects, we might expect to see even more obvious signs of artificial construction. The fact that the evidence is subtle and ambiguous argues against the object being a deliberately constructed probe, which presumably would have been designed for robustness and functionality, rather than being barely distinguishable from natural objects. Critics of the artificial hypothesis also pointed to the principle of parsimony. We know natural comets exist. We've observed thousands of them in our solar system. We have well-developed physical models of how comets form, evolve, and behave. Even if Atlas has unusual properties, it's simpler to assume it's an outlier among natural objects, rather than invoking an entirely new category of artificial interstellar probes, for which we have no confirmed examples. The history of astronomy provides many examples of phenomena that seemed mysterious or even supernatural before being explained naturally. Variable stars, pulsars, quasars, gamma-ray bursts all seemed inexplicable when first discovered. In each case, exotic explanations were proposed, sometimes involving civilizations or artifacts. In every case, natural explanations eventually prevailed. This historical pattern counsels patience and skepticism toward claims of artificial phenomena. While it doesn't prove Atlas is natural, it suggests we should exhaust natural explanations thoroughly before accepting unprecedented conclusions. And indeed, the natural explanations for Atlas, while requiring some special assumptions, were not yet exhausted. Researchers continued developing more sophisticated models, incorporating more physics, exploring larger parameter spaces. As debates continued about ATLAS's nature, some researchers proposed intermediate positions between purely natural and purely artificial explanations. These hybrid hypotheses suggested scenarios where Atlas might be partially shaped by intelligent processes without being a deliberately constructed probe. One such hypothesis proposed that ATLAS might be debris from an alien civilization, perhaps material ejected during mining operations, industrial processing, or even a catastrophic event like a war or accident. Such debris could have unusual properties reflecting its origin in technological processes, while not being a functional device with any purpose or capability. This scenario would explain why Atlas didn't respond to our observations or transmit detectable signals. It would be inactive material, not a working probe, but it could still have properties different from natural objects, unusual composition from industrial processing, regular shapes from having been machined or manufactured, surface coatings from exposure to artificial environments. The fragmentation pattern might reflect the object's origin as an aggregate of processed materials weakly bound together. The thermal and spectroscopic anomalies could indicate composition dominated by synthetic compounds or materials refined for particular purposes. The unusual acceleration profile might result from contamination with volatile substances used in industrial processes. This hypothesis had the advantage of explaining the anomalies without requiring Atlas to be a sophisticated, purposeful probe. It was a middle ground between claiming detection of alien technology and insisting everything must be natural. However, it still required accepting that we had encountered material from an extraterrestrial civilization, which remained an extraordinary claim. Another hybrid scenario suggested that ATLAS might be a natural object that had been modified or visited by intelligence at some point in its history. Perhaps it had served as a way station or resource depot during exploration of its home system. Perhaps it had been tagged with markers or instruments that failed long ago, but left behind structural or compositional signatures. This would make Atlas essentially natural in current state, but with a history involving intelligent interaction. The object's current behaviour would be dominated by natural processes, but subtle signatures of past modification might remain detectable to careful observers. This scenario would explain why the evidence for artificial origins is ambiguous rather than clear-cut. Some researchers explored the possibility that ATLAS might be an example of convergent evolution, a naturally formed object that coincidentally resembles what an artificial probe might look like. Just as certain crystalline minerals can form geometric shapes that look almost engineered, perhaps some rare combination of circumstances could produce a comet with properties mimicking artificial construction. This seems like a contrived explanation, requiring extensive coincidence, but it's worth noting that nature sometimes produces remarkably ordered structures through purely physical processes. Snowflakes have intricate geometric patterns. Some mineral formations show regular spacing and shapes. Biological structures often exhibit engineering-like optimization. If purely natural processes can create such order, perhaps a comet could have properties that misleadingly suggest intelligent design. The hybrid hypotheses were often viewed skeptically by both sides of the main debate. Those favouring natural explanations saw them as unnecessary complications, attempts to have it both ways without committing to a clear position. Those open to artificial explanations saw them as hedging, refusing to follow the evidence to its logical conclusion. But hybrid hypotheses served a useful purpose in the scientific discourse. They opened up conceptual space between the binary choice of natural versus artificial. They reminded everyone that the universe offers more possibilities than our categorical thinking sometimes allows. And they highlighted how difficult it is to definitively categorize an object based on limited observations of inherently ambiguous phenomena. The debate over hybrid hypotheses reflected deeper questions about what constitutes a natural versus artificial object. Is a beaver dam natural or artificial? It's created by biological activity for functional purposes, but beavers are natural organisms. If an asteroid were captured and used as a space station, then abandoned for millions of years until all technology had eroded away, would the asteroid be natural or artificial? These philosophical questions might seem abstract, but they're relevant to how we interpret observations. Our categories are human constructs imposed on a continuous reality. An object might fall into grey areas, having properties that don't fit neatly into our preconceived boxes. Atlas might be one such object, resisting simple categorization and forcing us to think more carefully about our assumptions and definitions. As the debate over ATLAS continued, some researchers began examining not just the object itself, but the processes by which scientists were interpreting the data. This meta-analysis revealed interesting patterns in how biases and preconceptions shaped different researchers' conclusions. Cognitive psychology has shown that humans are subject to numerous biases when evaluating evidence. Confirmation bias leads us to preferentially notice and remember information that supports our existing beliefs. Availability bias causes us to overweight vivid or recent examples. Anchoring bias makes our judgments dependent on initial framing. Scientists are not immune to these biases. While scientific training and peer review provide some protection, biases can still influence which hypotheses researchers consider plausible, how they design their analyses, and how they interpret ambiguous results. Understanding these biases is important for evaluating scientific debates fairly. Some researchers who were initially skeptical of artificial explanations displayed what might be called a normalcy bias, a tendency to assume that new phenomena will resemble familiar ones. Because all previously observed comets and asteroids were natural, the default assumption was that Atlas must be natural too. Any unusual properties must have natural explanations, even if those explanations required special assumptions. Conversely, some researchers who were more open to artificial explanations might have been influenced by what could be called the novelty bias, a preference for exciting or unconventional interpretations. The possibility of detecting an alien artifact is scientifically thrilling, and this excitement might subtly influence how one interprets ambiguous evidence, making unusual properties seem more significant than they might be. Neither bias is necessarily wrong or bad. They're natural human tendencies that affect reasoning in subtle ways. The key is recognizing their influence and trying to compensate for them, to evaluate evidence as objectively as possible, despite the psychological predispositions we all carry. One way researchers tried to mitigate bias was through blind or double-blind analysis techniques. Some teams analysed atlases' properties without initially being told which object they were studying, to prevent preconceptions about its interstellar nature from influencing their conclusions. Others developed statistical tests first and committed to specific interpretations of results before seeing the actual data. These methodological safeguards helped but couldn't eliminate bias entirely. The very choice of which analyses to perform, which questions to ask, reflects underlying assumptions and interests. A researcher focused on natural explanations might invest effort in modelling exotic cometary processes, while one open to artificial explanations might focus on searching for signals or geometric regularities. The sociology of science also played a role. Researchers who proposed artificial explanations risked their professional reputations, potentially being labelled as fringe or sensationalist by colleagues. This social pressure encourages conservatism, makes researchers hesitant to advocate for unconventional interpretations, even when evidence might support them. Conversely, there could be subtle incentives toward making provocative claims, as controversial ideas attract media attention and public interest, potentially leading to more citations, speaking invitations and book deals. A researcher proposing that Atlas might be artificial would certainly get more attention than one confirming it was a normal comet. Navigating these competing pressures requires careful judgment and intellectual integrity. The ideal is to follow evidence wherever it leads, regardless of whether conclusions are conventional or controversial, safe or risky. In practice, this ideal is difficult to achieve because humans are social creatures whose thinking is inevitably influenced by cultural and professional contexts. Some of the most productive researchers on Atlas were those who explicitly acknowledged uncertainty and avoided strong commitments to any particular interpretation. They presented evidence, discussed multiple hypotheses, and emphasized what additional observations would help discriminate between possibilities. This modest approach, while less attention-grabbing than confident declarations, better reflected the genuine state of knowledge. The debate over Atlas thus became not just about the object itself, but about how science works when dealing with genuinely ambiguous phenomena at the frontiers of knowledge. It highlighted both the strengths of the scientific method and its limitations, showing how careful observation and rigorous analysis can constrain possibilities, while also revealing how much room for interpretation remains when evidence is incomplete and ambiguous. As Atlas faded from view in early 2020, having fragmented and dispersed to the point where even the largest telescopes could no longer detect it clearly, the scientific community found itself in a frustrating position. The object had posed intriguing questions but provided insufficient data for definitive answers. Now it was gone, its fragments continuing their journeys into the outer solar system and eventually back into interstellar space, carrying their secrets with them. This experience highlighted a fundamental challenge in studying interstellar objects. They appear suddenly, remain observable for only a few months, and then disappear. Often forever. The window for gathering data is brief, and once it closes, no amount of theoretical work can compensate for observations not made. In Atlas's case, there were numerous observations that could have been performed but weren't, often due to time constraints, scheduling conflicts, or simply not recognizing what would be important until after the opportunity had passed. Higher resolution imaging might have revealed surface features, More extensive spectroscopy could have better constrained composition. Polarimetric observations at more wavelengths might have clarified particle properties. The lesson learned was that future interstellar visitors needed to be observed as comprehensively as possible during their brief passages. This led to the development of target-of opportunity programs at major observatories, pre-approved plans that could be activated quickly when interesting objects appeared. Funding agencies began recognizing the unique scientific value of interstellar objects and the need for rapid response capabilities. But even with better preparedness, the fundamental problem remained. Interstellar objects are transient phenomena, and our observations will always be limited by the brief time they're accessible. This means we may never definitively resolve questions about objects like Atlas. We'll have better data on future visitors, but each object might pose its own unique puzzles that can't be fully solved before it departs. This situation requires a shift in how we think about studying these objects. Rather than expecting to fully understand each individual visitor, we need to build up statistical knowledge from multiple observations. Each object contributes pieces to the puzzle, and only by combining information from many visitors will we construct a comprehensive picture of the interstellar population. In the case of the artificial hypothesis, this means that no single object is likely to provide conclusive proof one way or another. What we need is to observe many interstellar objects and see what fraction display anomalous properties. If all interstellar visitors are weird in their own ways, that suggests natural processes produce more diversity than we've appreciated. If most are clearly natural and only rare outliers show anomalies, that might strengthen the case for unusual origins of those outliers. The detection rate of interstellar objects was expected to increase dramatically with new telescopes coming online. The Vera C. Rubin Observatory, beginning operations in the mid-2020s, was predicted to detect dozens of interstellar visitors per year once fully operational. This would quickly build up a statistical sample large enough for meaningful conclusions. Some researchers began compiling catalogues of properties that should be measured for each newly detected interstellar object, creating standardized observation protocols to ensure consistent data collection. This would allow fair comparisons between objects and identification of patterns that might not be apparent from individual cases. There was also hope that spacecraft missions might eventually intercept an interstellar visitor. Such missions would be challenging, requiring rapid development and launch to catch objects moving quickly through the solar system. But the scientific return would be immense, providing close-up observations impossible to achieve from Earth-based telescopes. NASA and other space agencies studied concepts for intercept missions, exploring what would be technically feasible with current or near-future rocket technology. The basic conclusion was that with sufficient warning and advanced preparation, interception missions were possible for objects that passed relatively close to Earth and arrived from favourable directions. If such a mission ever reached an interstellar object, it could directly test hypotheses about natural versus artificial origins. Close-up imaging would reveal surface details. Physical sampling could analyse composition precisely. Instruments could search for electromagnetic emissions or other signatures that Earth-based observations might miss. Until such missions become reality, we remain dependent on telescopic observations, always limited by distance and the brief observing windows. The fragments of ATLAS continue their journeys, perhaps carrying answers to the questions they raised, but those answers are now beyond our reach, at least for the foreseeable future. The debate over Atlas's nature, regardless of how it eventually resolves, has implications that extend far beyond this single object. It touches on fundamental questions about our place in the universe, the prevalence of life and technology, and how we should approach evidence for extraordinary phenomena. If Atlas were indeed artificial, it would be one of the most significant discoveries in human history, comparable to or exceeding the detection of radio signals from an extraterrestrial civilization. It would prove that technological intelligence exists elsewhere in the universe, and that such civilizations engage in some form of interstellar exploration, whether through probes, artifacts, or debris. This would immediately raise further questions. How common are technological civilizations? If we detected one artifact among 3 interstellar objects, does that imply civilizations are numerous and exploration common? Or were we extraordinarily lucky, encountering a rare outlier? What does the apparent age and inactive state of the artifact tell us about the longevity of civilizations or the typical fate of their technology? The fact that Atlas appeared inactive, showing no signs of purposeful behaviour or communication, would itself be informative. It might suggest that interstellar probes, if they exist, are typically ancient and non-functional by the time they encounter other stellar systems. Or it might indicate that hypothetical probes are designed to be passive, observing without interacting, making them difficult to distinguish from natural objects. On the other hand, if ATLAS is eventually confirmed to be entirely natural, that too would be significant. It would teach us that interstellar objects can have more diverse properties than we'd appreciated, that our understanding of comets and their behaviour needs expansion to account for more exotic possibilities. A natural atlas would also inform the ongoing search for extraterrestrial intelligence. It would provide a cautionary example of how natural phenomena can produce signatures that might be mistaken for artificial ones. This would help SETI researchers refine their criteria for what constitutes convincing evidence of technology, reducing false positives while hopefully not missing genuine signals. The epistemological questions raised by ATLAS are perhaps equally important. How should science deal with claims that are extraordinary but not definitively falsifiable? How much evidence is sufficient to take unusual hypotheses seriously? When does openness to unconventional ideas cross into credulous acceptance of insufficiently supported claims? These questions don't have simple answers. Science works best when dealing with repeatable phenomena that can be studied systematically with controlled experiments. But much of astronomy deals with unique or rare events observed from a distance with limited data. In such contexts, definitive proof is often impossible, and researchers must make judgments based on incomplete information. The Atlas case illustrates these challenges. The evidence is genuinely ambiguous. Reasonable, informed researchers examining the same data reach different conclusions based on different background assumptions and different weightings of various pieces of evidence. There's no objective algorithm that can definitively determine the truth. Human judgment, with all its limitations and biases, remains essential. This reality might be uncomfortable for those who prefer science to provide clear, unambiguous answers. But it's important to recognise that uncertainty and debate are normal and even healthy parts of the scientific process, especially when dealing with frontier questions where knowledge is limited. The public reaction to the Atlas debate was mixed. Some found the possibility of an alien artifact thrilling, evidence that we're not alone in the universe. Others were sceptical, viewing claims of artificial origins as premature or sensational. Many simply found the whole discussion confusing, uncertain how to evaluate competing claims from scientists who seemed equally credible. This highlights the challenge of science communication, particularly for complex, ambiguous topics, the nuances that scientists debate. The careful qualifications and conditional statements often get lost in translation to public discourse. Headlines simplify and sensationalize. Uncertainties are either exaggerated into complete ignorance or dismissed to present false certainty. Researchers studying Atlas tried various approaches to communicating their work responsibly. Some emphasized what was known for certain, the observational facts, while clearly distinguishing these from interpretations and speculations. Others focused on the process of scientific reasoning, explaining how different hypotheses are developed and tested. A few engaged directly with the public's excitement or skepticism, acknowledging emotions while gently steering toward rational evaluation of evidence. The experience gained from the ATLAS case will inform future discussions about interstellar objects and other potentially anomalous astronomical phenomena. As our detection capabilities improve and the catalogue of interstellar visitors grows, we'll likely encounter more objects with unusual properties that challenge explanation. The frameworks for thinking about such cases, both scientifically and in terms of public communication, are being developed now through examples like ATLAS. The questions raised by Atlas connect to one of the deepest puzzles in astrobiology, the Fermi paradox. This paradox, named after physicist Enrico Fermi, asks why we haven't detected obvious signs of extraterrestrial civilizations if they're likely to be common in the universe. The basic reasoning goes like this. The galaxy is very old, about 13 billion years. Stars with planets have existed for most of that time. If intelligent life arises readily on suitable planets, and if some fraction of intelligent species develop technology, then technological civilization should be widespread, even if interstellar travel is difficult. Civilizations have had billions of years to spread through the galaxy. If civilizations are widespread and long-lived, we might expect to see evidence of their presence, megastructures, artificial signals, probes exploring other stellar systems. Yet we detect none of these things. The galaxy appears natural, with no obvious signs of technological civilization beyond Earth. This is the Fermi paradox. The apparent contradiction between the expectation of a widespread life and the absence of evidence for it. Numerous solutions to the Fermi paradox have been proposed. Perhaps life is rare, arising only under very specific conditions that are seldom met. Perhaps intelligence is rare, requiring unlikely evolutionary paths. Perhaps technology is rare, with most intelligent species never developing radio transmitters or spaceflight. Or perhaps civilizations are common but short-lived, destroying themselves or collapsing before achieving interstellar expansion. Perhaps they're common, but choose not to engage in obvious activities like building megastructures or broadcasting powerful signals. Perhaps they exist but in forms we don't recognize, or at scales we haven't considered. A TLAS, if artificial, would provide a data point relevant to the Fermi paradox. It would show that at least one civilization sent probes or debris into interstellar space that could potentially be detected by others. This suggests that interstellar exploration, or at least material exchange, does occur, that technological civilizations don't all remain confined to their home systems. However, the apparently inactive state of Atlas would also be informative. If probes are sent but they're ancient and non-functional when encountered, this might indicate that civilizations don't maintain active networks of probes, that exploration is a brief phase rather than an ongoing activity, or that the challenges of maintaining technology over interstellar timescales are greater than might be hoped. The fact that we've potentially detected one artificial object among only 3 confirmed interstellar visitors would suggest that either debris from technological civilizations is relatively common in the galaxy, or we've been remarkably lucky in our limited sample. The former possibility would indicate that many civilizations produce interstellar artifacts. The latter would make detection statistics essentially meaningless. Alternatively, if ATLAS is natural, its unusual properties might suggest that we need to be more careful about what we interpret as potentially artificial. Natural objects can display surprising characteristics, and we might need stronger evidence before concluding that something is technological in origin. This would make solving the Fermi paradox harder, as it would raise the bar for what constitutes convincing evidence of extraterrestrial technology. Some researchers have proposed that interstellar space might be filled with technological debris from civilizations throughout the galaxy's history. Failed missions, discarded equipment, waste material, all could be wandering between stars. If so, then encountering such debris might be more likely than encountering functional probes or receiving intentional signals. This scenario would partially resolve the Fermi paradox by suggesting that technological artifacts are present but difficult to recognize. They're not signaling, they're not obviously artificial, they're just debris indistinguishable from natural objects without close examination. Atlas, in this view, might be one piece of a vast cloud of material, most of which we'll never identify as artificial, because it lacks dramatic signatures. However, this scenario requires that producing interstellar debris is common among civilizations, which itself might tell us something about typical technological development. Do civilizations typically go through phases of extensive space activity that generate significant debris? Or would most civilizations be more careful, either remaining near their homeworlds or cleaning up after their explorations? The connection between Atlas and the Fermi paradox illustrates how astronomical observations can inform philosophical questions about life in the universe. Whether Atlas is natural or artificial, studying it contributes to our understanding of what's possible, what's likely, and what we should expect as we continue searching for evidence of life beyond Earth. If we seriously entertain the possibility that ATLAS might be artificial, we must contemplate what kind of technology could create such an object and what purposes it might serve. This speculation is necessarily uncertain, but it can be grounded in physics and in our understanding of what would be practically achievable by a sufficiently advanced civilization. One possibility is that ATLAS could be a probe designed for scientific exploration. Such a probe might be sent from its home system to visit other stars, gathering data about their planetary systems. If it were intended to operate for millions of years across interstellar distances, it would need to be robust, self-maintaining, and capable of operating autonomously. The fragmentation we observed might not be failure, but rather a deliberate strategy. A probe that splits into multiple components could survey a larger volume of space, with fragments taking different trajectories to sample different regions of the target system. The regular spacing and similar sizes of Atlas's fragments would make sense in this context, representing pre-planned separation rather than chaotic breakup. The lack of detected signals could indicate that the probe was designed for passive observation rather than active communication. It might be collecting data silently, either storing it for later retrieval or transmitting using methods we can't detect. Or it might be so ancient that its communication systems have failed while the basic structure remains intact. Another possibility is that Atlas might be a von Neumann probe, a self-replicating machine. Such probes, proposed by mathematician John von Neumann, could theoretically explore an entire galaxy using a relatively modest initial investment. A civilization would send out several probes. Each probe reaches a new stellar system, uses local materials to build copies of itself, and sends those copies to additional systems. The process repeats, leading to exponential growth in the number of probes. If Atlas were a von Neumann probe or a fragment thereof, its fragmentation might represent a malfunction in the replication process, an attempt to divide that went wrong due to damage accumulated over interstellar travel. The unusual material properties might reflect the probe's composite nature, assembled from various materials harvested in previous stellar systems. The challenge with the von Neumann probe hypothesis is that such probes should be enormously abundant if any civilization ever developed them. They would spread exponentially, eventually filling the galaxy. The fact that we haven't detected obvious swarms of self-replicating probes is often cited as evidence against this scenario. However, if the probes are designed to be inconspicuous, or if they've mostly failed after billions of years, they might be present but not obviously detectable. A less exotic possibility is that ATLAS could be debris, material discarded or lost during space activities. Advanced civilizations might engage in mining operations in their own or other stellar systems, processing asteroids or comets for resources. The waste products or lost equipment from such operations could end up on interstellar trajectories. This would explain why Atlas appears inactive and shows no signs of purposeful behavior. It would just be trash, of no more interest to its creators than our own defunct satellites are to us. But to us, encountering material processed by another civilization would be scientifically invaluable. Providing direct evidence of extraterrestrial technology, even if the technology itself is degraded or discarded. Some researchers have speculated about more exotic possibilities. Could ATLAS be a solar sail? a device designed to be pushed by starlight for propulsion. The fragmentation might represent deployment of thin membranes that appear as separate objects when viewed from Earth. The unusual acceleration profile could result from the changing orientation of sail components as they deploy and maneuver. Or could Atlas be something entirely different, a technology we can't even conceptualize because it operates on principles unknown to us? This possibility is acknowledged but doesn't lead anywhere productive. If the technology is truly beyond our understanding, we can't develop specific hypotheses to test. The most honest position might be to say that if Atlas is artificial, we don't know what it is or what its purpose might have been. We can imagine scenarios based on our own technology extrapolated forward, but an actual alien artifact might be as incomprehensible to us as a smartphone would be to a medieval scholar. We might recognize that it's artificial without understanding what it does or how it works. This uncertainty shouldn't prevent speculation or hypothesis development. Even if we can't definitively determine the nature of a hypothetical artifact, thinking through possibilities helps us develop expectations for what artificial objects might look like and what observations would help distinguish them from natural phenomena. The exercise is valuable even if it doesn't yield definitive answers for Atlas specifically. Beyond the scientific and technical questions, Atlas raises profound philosophical issues about humanity's place in the cosmos and how we should respond to the possibility of encountering evidence of other civilizations, even in the form of ancient inactive artifacts. The philosophical question of whether we're alone in the universe is one of the oldest and deepest that humans have contemplated. For most of history, this question was purely speculative, unanswerable through observation or evidence. Only in recent decades has technology advanced to the point where we can actually search for signs of extraterrestrial life and intelligence. Detection of an alien artifact, even an inactive one, would fundamentally change this question. It would transform Quote 2 from an open philosophical question into a settled matter of fact. We would know with certainty that intelligence has arisen elsewhere, that technology has been developed beyond Earth, that the universe contains or contained civilizations other than our own. This knowledge would have profound psychological and cultural impacts. For some, it would be validating, confirming a long-held intuition that the universe is teeming with life. For others, it might be unsettling, challenging notions of human specialness or raising concerns about our vulnerability. The discovery would likely become a defining moment in human history, reshaping how we see ourselves and our future. However, discovering an inactive artifact would be different from establishing communication with an active civilization. We would know they exist or existed, but we wouldn't know where they are now, whether they still exist, what they're like, or what they might think of us. The artifact would raise as many questions as it answered, perhaps leaving us more tantalized than satisfied. Some philosophers have argued that discovering evidence of extinct civilizations might be more disturbing than finding no evidence at all. If civilizations arise but typically fail or vanish, leaving only ruins and debris, this would be a pessimistic message about the long-term prospects for technological intelligence. It would suggest that the challenges facing civilizations, whether self-destruction, resource depletion, or other factors, are typically insurmountable. Others counter that even an inactive artifact would be hopeful in its own way. It would show that intelligence can arise, that technology can be developed, that exploration can be undertaken. The fact that a particular civilization might no longer exist doesn't negate the possibility that others continue. It simply shows that the universe is old and full of history, with countless stories of which we're seeing only fragments. The ethical questions raised by a potential artifact are also complex. If Atlas were confirmed to be artificial, should we attempt to study it aggressively, perhaps even trying to intercept and retrieve it for detailed examination? Or would this be disrespectful, interfering with an object that might have cultural or historical significance to its creators, assuming they still exist somewhere? Some argue that the scientific value would justify any reasonable effort to study an artifact as thoroughly as possible. Others suggest we should be more cautious, considering that the artifact might be more than just a passive object. It might have purposes or functions we don't understand, and interfering with it could have unintended consequences. There's also the question of how knowledge about ATLAS should be disseminated. Should preliminary findings be shared immediately with the public, or should confirmation be achieved before making announcements? The astronomical community generally favours transparency, but with such a potentially momentous discovery, there are arguments for careful verification before creating public excitement that might not be warranted. The ATLAS case has illustrated these dilemmas in real time. The unusual observations were published in scientific journals and discussed at conferences, making them part of the public record. But researchers were careful to emphasise uncertainties, to avoid claiming definitive conclusions prematurely. This balance between openness and caution is difficult to maintain, especially when media and public interest are intense. Perhaps the deepest philosophical question is epistemological. How do we know when we've found genuine evidence of extraterrestrial technology versus a natural phenomenon we don't yet fully understand? This question has no simple answer. It requires balancing skepticism with openness, demanding high standards of evidence while remaining willing to accept unprecedented conclusions when evidence truly warrants them. The Atlas case may ultimately serve as a valuable philosophical exercise even if it's never definitively resolved. It forces us to confront these questions seriously, to think through how we would evaluate evidence, what standards we should apply, and how we should respond to ambiguous situations where extraordinary and ordinary explanations both remain viable. As the specific case of Atlas faded from immediate attention, having fragmented and dispersed beyond detection, the broader question remained: what should we expect from future interstellar visitors, and how should we prepare to study them? The lessons from ATLAS were being incorporated into planning for future observations. Survey telescopes were being programmed with better algorithms for detecting interstellar objects early, when they're still approaching and will remain observable for months. Protocols were being developed for rapid characterization of newly discovered visitors, ensuring that key measurements are prioritized. One significant development was the creation of international coordination networks specifically for interstellar objects. When a new visitor is detected, alerts go out immediately to observatories worldwide. Pre-approved observing programs can be activated within hours. Data is shared rapidly through common repositories. This coordination aims to maximize the scientific return from each visitor's brief passage through the observable solar system. Researchers were also developing more sophisticated theoretical frameworks for interpreting observations of interstellar objects. What properties would definitively indicate artificial origins? What observations would rule out natural explanations? What signatures might we expect from different types of hypothetical artifacts or probes? This theoretical work is essential for ensuring that when we encounter genuinely anomalous objects in the future, we'll recognize them as such and know what additional observations to pursue. It's also important for avoiding false positives, for not claiming artificiality when natural explanations remain viable. Some teams were working on machine learning approaches, training algorithms to recognize patterns in observational data that might indicate artificial objects. The algorithms could be trained on simulations of both natural and hypothetical artificial objects, learning to distinguish between them based on subtle combinations of properties. While such algorithms can't replace human judgment, they might help identify the most interesting targets for detailed study. There was also growing interest in spacecraft missions to intercept interstellar objects. Several mission concepts were being studied in detail, exploring different approaches to rendezvousing with fast-moving visitors. The technical challenges are significant, but not insurmountable with existing technology, especially if we have years of warning from early detection. One proposed approach involves keeping a spacecraft in a ready state, prepared for rapid launch when an interesting interstellar object is detected on a favourable trajectory. The spacecraft would be relatively simple, carrying cameras and basic instruments. designed for rapid deployment rather than comprehensive scientific study. Even limited close-up observations would be far better than what we can achieve from Earth. More ambitious concepts envision larger spacecraft with more capable instruments, possibly even including sample return capability. Such missions would be much more expensive and couldn't be kept in ready state indefinitely. They would need to be developed and launched in response to specific targets, requiring years from decision to intercept. This would only be possible for objects detected very early, years before their closest approach to the Sun. The economic and political challenges of mounting such missions are significant. Space agencies must balance competing priorities, and an intercept mission would require substantial resources that might otherwise support other scientific efforts. Building support for such investments requires demonstrating that interstellar objects are scientifically valuable enough to warrant the expense. The Atlas case, with all its mysteries and debates, actually helped make this case. It showed that interstellar visitors can have properties we don't fully understand, that they raise genuine scientific questions that can only be answered through careful study. Even if Atlas itself was natural, it demonstrated that the category of interstellar objects includes enough diversity and potential for surprises that detailed study is justified. Looking ahead, the rate of interstellar object discoveries was expected to increase dramatically. The Vera Rubin Observatory, scheduled to begin full operations in the mid-2020s, would scan the sky repeatedly, detecting fainter and more distant objects than previous surveys. Estimates suggested it might detect dozens of interstellar visitors per year. With such a catalogue, statistical analysis would become possible. We could determine what fraction of interstellar objects show anomalous properties. We could look for patterns in their properties, correlations between different observables. We could better constrain the population of interstellar objects and understand their diversity. If objects like Atlas, with its unusual characteristics, turn out to be rare, that would strengthen the argument that such objects deserve special attention and might potentially be artificial. If objects like Atlas turn out to be common, it would suggest that interstellar comets are more diverse than our limited solar system sample indicated. And unusual properties aren't necessarily indicators of artificial origins. Either way, the growing catalogue of interstellar visitors will transform our understanding. We're moving from the era of studying individual peculiar objects to the era of population statistics and comparative analysis. This transition will enable science that simply wasn't possible when we had only 2 or 3 examples to consider. As we approach the end of our exploration of Atlas's mysteries, it's important to acknowledge something that science sometimes struggles with: uncertainty. Despite all the observations, all the analysis, all the debate, we don't have definitive answers about ATLAS's nature. We may never have them. This is uncomfortable for those who prefer clear conclusions. In our daily lives, we're accustomed to finding answers to questions, resolving ambiguities, reaching decisions. But the universe doesn't always cooperate with our desire for certainty. Sometimes the evidence is genuinely ambiguous, supporting multiple interpretations without decisively favouring any particular one. A TLAS represents such a case. The natural explanations require assuming several unusual properties, each individually plausible but collectively forming a somewhat contrived picture. The artificial explanation requires accepting something unprecedented, invoking a category of objects we've never confirmed exists. Neither option is clearly superior based solely on the available evidence. In situations like this, the honest scientific position is to acknowledge uncertainty rather than forcing a conclusion. We can say, here's what we observed, here are the possible explanations, here's how well each explanation fits the data, and here's what additional observations might help resolve the ambiguity. This doesn't mean throwing up our hands and claiming we know nothing. We know quite a bit about ATLAS's properties and behaviour. It means recognising the limits of what we can conclude from limited data. This acceptance of uncertainty is actually a strength of the scientific method, not a weakness. Science doesn't claim to have all the answers. or to reach conclusions with absolute certainty. It provides frameworks for evaluating evidence and updating beliefs as new information becomes available. It's comfortable with provisional conclusions, with saying, based on current evidence, this seems most likely, but we could be wrong. The alternative, insisting on definitive answers when evidence is ambiguous, leads to false certainty. It can mean committing prematurely to explanations that later prove wrong, or dismissing possibilities that eventually turn out to be correct. Maintaining appropriate uncertainty, while sometimes frustrating, is more intellectually honest and ultimately more productive. For Atlas specifically, the uncertain status is likely to persist indefinitely. The object and its fragments have faded beyond detection. No new observations will be forthcoming unless the fragments somehow become visible again, perhaps if they pass very close to Earth in the distant future, which seems unlikely given their trajectories. The data we have is all the data we're likely to get. Future observations of other interstellar objects might provide relevant context. If we observe many more visitors and all show similar unusual properties to Atlas, that would strengthen natural explanations by suggesting such properties are common among interstellar comets. If most future visitors appear conventionally normal and only rare outliers show anomalies, that might strengthen suspicions about those unusual cases. But each interstellar object is unique, and observations of others won't definitively resolve questions about Atlas itself. We'll be left with our incomplete dataset and the various interpretations of it. Different researchers will continue to favour different explanations based on their own weightings of evidence and their prior beliefs about what's likely. This situation is more common in science than popular portrayals sometimes suggest. While some questions can be answered definitively through careful experiments or observations, many others remain ambiguous, with competing theories each having strengths and weaknesses. Progress comes not from resolving all questions, but from gradually accumulating knowledge that narrows possibilities and constrains explanations. The Atlas case will likely remain in the category of unresolved mysteries, cited by different researchers as either an example of an unusually diverse natural object or as a potential artifact that warrants serious consideration. It will appear in discussions of how to recognize artificial objects and in debates about the appropriate standards of evidence for extraordinary claims. In the end, perhaps the most important lesson from ATLAS is about how we approach the unknown. When we encounter phenomena we don't fully understand, we have choices about how to respond. We can dismiss mysteries as likely mundane, requiring no special attention. We can embrace extraordinary explanations uncritically, letting excitement override rigour. Or we can walk a middle path, taking anomalies seriously while maintaining skepticism, following evidence carefully while acknowledging its limitations. This middle path is difficult. It requires intellectual humility, comfort with uncertainty, and willingness to entertain possibilities that might seem unlikely without committing to them prematurely. But it's the path that best serves the goal of understanding reality as it actually is, rather than as we might prefer it to be. Atlas, whether ultimately natural or artificial, has pushed us to walk this path, to grapple with genuine ambiguity, and to develop frameworks for doing so rigorously. In this sense, the object has already made a valuable contribution to science, regardless of how its particular mysteries eventually resolve. As we shift our perspective from the technical details to the broader meaning, there's something profoundly beautiful about the questions Atlas has raised, regardless of the answers. The simple fact that we can ask whether an object from beyond our solar system might be artificial represents a remarkable moment in human development. For most of human history, the possibility of encountering evidence of extraterrestrial intelligence was purely philosophical. We could imagine other worlds, other civilizations, but we had no way to actually look for them. The universe beyond Earth was inaccessible, knowable only through mythology and speculation. Now, we have telescopes sensitive enough to detect small objects passing through the solar system from interstellar space. We have instruments capable of analysing their composition and motion. We have mathematical frameworks for understanding their origins and predicting their futures, and we have accumulated enough knowledge about natural processes to recognise when something might not fit our expectations. This capability represents the culmination of centuries of scientific and technological development. Galileo pointed his telescope at the heavens 400 years ago, revealing mountains on the moon and moons around Jupiter. Slowly, generation by generation, we've built up understanding and capability until we've reached this point, detecting visitors from other stellar systems and contemplating whether they might be more than natural objects. The fact that we can seriously consider this question, that we have the tools and knowledge to investigate it rather than merely speculating, is itself remarkable. It doesn't matter whether Atlas is actually artificial. The importance lies in the fact that we can ask the question meaningfully, that we've reached a level of understanding where such questions are investigable rather than purely philosophical. This capability will only improve with time. Future telescopes will be more sensitive, detecting smaller and more distant objects. Future instruments will provide more detailed characterization. Future spacecraft might visit interstellar objects directly. Examining them close up, each advance expands the questions we can ask and potentially answer. There's also beauty in the interdisciplinary nature of studying these objects. Understanding Atlas requires astronomy to detect and track it, physics to model its motion and thermal properties, chemistry to interpret its composition, statistics to evaluate unusual patterns, and even philosophy to think carefully about what constitutes convincing evidence for extraordinary claims. No single discipline has all the answers. Progress requires collaboration, people with different expertise working together, each contributing their perspective. The debates about Atlas's nature have brought together observers and theorists, specialists in comets and specialists in orbital mechanics, astrobiologists and planetary scientists, all examining the same phenomenon from their different vantage points. This collaboration across disciplines and across national boundaries reflects one of the best aspects of science. While individual researchers might compete for recognition or funding, the broader enterprise is fundamentally cooperative. Data is shared, observations are published, arguments are made transparently so others can evaluate them. The goal is collective understanding rather than individual glory. The questions Atlas raises also connect to deep human yearnings. We've always wondered whether we're alone, whether intelligence exists elsewhere in the cosmos. For some, this wondering comes from a sense that the universe seems too vast to contain only us. For others, it comes from loneliness, a desire for companionship in an apparently empty cosmos. For still others, it's pure curiosity, wanting to know what's true regardless of implications. Whatever the motivation, the question matters to us in ways that transcend pure science. It touches on meaning and purpose, on our place in the cosmic story. Discovering that we're not alone would reshape how we understand ourselves. Even discovering evidence of civilizations that existed but no longer do would transform our perspective, showing that intelligence is possible, but perhaps challenging to maintain. The beauty is that we can actually investigate these questions now. We're not limited to speculation. We can build instruments, make observations, analyze data, and gradually narrow the space of possibilities. We might not get final answers in any individual case like Atlas, but we're making progress, accumulating knowledge, building understanding piece by piece. This process of discovery, of gradually illuminating what was previously dark and unknown, is one of humanity's great achievements. Each generation knows more than the previous one, sees further, understands deeper. We stand on the shoulders of giants, as Newton said, and will be shoulders for future generations to stand on in turn. It's worth reflecting on how recently our ability to detect and study interstellar objects has developed. The timeline is remarkably compressed, with most of the relevant capabilities emerging only in the last few decades or even years. The first confirmed interstellar object, Oumuamua, was detected only in 2017, less than a decade ago. Before that, While theoretical models predicted that interstellar visitors should exist, we'd never actually seen one. The detection of Oumuamua opened a new era, proving that these theoretical predictions corresponded to real phenomena. The technology that enabled Oumuamua's discovery was itself recent. The Pan-STARRS telescope that detected it came online in 2010. Its automated survey capability, repeatedly imaging the sky and using software to identify moving objects, represented the culmination of decades of development in telescope design, digital cameras, and computer analysis. Borisov was discovered in 2018 using amateur equipment. A testament to how accessible advanced astronomical observation has become. A dedicated amateur astronomer, building his own telescope and conducting systematic surveys, could detect an object that would have been invisible to the greatest observatories of previous centuries. Atlas was detected in 2019 by a telescope network specifically designed to find potentially hazardous asteroids. The fact that the same system could detect both Earth-threatening near objects and distant interstellar visitors shows how versatile modern survey systems have become. The instruments used to study these objects are similarly recent. Spectroscopy has existed for over a century, but the sensitivity and sophistication of modern spectrographs vastly exceeds what was available even a few decades ago. The ability to detect faint spectral features from tiny distant objects requires both large telescopes and advanced instrumentation, capabilities that have only recently come together. If Atlas had passed through the solar system a century ago, we wouldn't have detected it at all. It would have come and gone without humanity ever knowing of its existence. 50 years ago, we might have detected it as a moving point of light, but we couldn't have determined it was interstellar or studied its properties in detail. 20 years ago, we would have had better capabilities, but still limited compared to what we had in 2019. This rapid advancement shows no signs of stopping. The Vera Rubin Observatory, expected to revolutionize detection of transient and moving objects, represents another leap forward in capability. The James Webb Space Telescope provides unprecedented infrared sensitivity for characterizing distant objects. Ground-based observatories continue to be built or upgraded with increasingly sophisticated instruments. Each technological advance expands what we can detect and study. Objects that were previously invisible become accessible. Properties that were previously unmeasurable become quantifiable. Questions that were previously purely theoretical become empirically testable. Looking forward, we can anticipate capabilities that will seem remarkable by current standards. Future telescopes might detect interstellar objects while they're still years away from the solar system, providing unprecedented time for observation and even for mounting spacecraft missions. Future instruments might characterize these objects in detail that currently seems impossible, determining their composition, structure, and history with precision. There's also the possibility of future breakthrough technologies we can't yet envision. Each generation of scientists tends to assume that current technology is approaching fundamental limits, only to be surprised by innovations that open entirely new possibilities. The scientists of the early 20th century couldn't have imagined spacecraft, radio telescopes, or digital imaging. We similarly might not be able to imagine what tools our descendants will have for studying the universe. This perspective on the timeline of capability provides context for the Atlas case. We're still in the very early stages of studying interstellar objects. We've detected only a handful of examples using newly developed capabilities. Our understanding is necessarily preliminary, based on limited data and evolving techniques. Future generations will look back on this era as the beginning of interstellar object science, the pioneering phase when the first examples were detected and characterized with primitive tools by today's standards. They'll probably find some of our conclusions amusingly wrong, limited by what we didn't know or couldn't measure. But that's how science progresses. Each generation does the best it can with available tools and knowledge, making mistakes and discoveries that the next generation builds upon. The fact that our current understanding is incomplete doesn't diminish its value. We're laying foundations, establishing baselines, developing methodologies that will be refined and extended by those who come after us. The story of Atlas is part of this larger story of humanity gradually expanding its understanding of the cosmos. Whether the object itself was natural or artificial matters less than what its study teaches us about how to investigate such questions, what observations to prioritize, what standards of evidence to apply, and how to think carefully about phenomena at the boundaries of our knowledge. Beyond the scientific and philosophical dimensions, there's an emotional aspect to the Atlas story worth acknowledging. The possibility, however remote, that we might have encountered an alien artifact evokes powerful feelings in people, feelings that shape how we engage with the topic and interpret the evidence. For some, the idea of alien artifacts is thrilling, exciting in a way that natural phenomena, however interesting, are not. The prospect of discovering evidence of extraterrestrial intelligence taps into a sense of wonder, a feeling that we're on the cusp of something momentous. This excitement can be so powerful that it affects judgment, making us see patterns where none exist, or interpreting ambiguous evidence favourably toward the conclusion we hope for. For others, the idea is unsettling rather than exciting. If alien artifacts exist in our solar system, what does that imply about the galaxy's population of technological civilizations? If such civilizations are common but leave only inactive debris, that's a pessimistic message about longevity of intelligence. If they're uncommon but we've already encountered one, that's extraordinarily lucky, perhaps implausibly so. Either way, it raises uncomfortable questions about humanity's future and our place in a cosmos that might be filled with ruins. There's also the emotional weight of uncertainty itself. Some people are comfortable with ambiguity, able to hold multiple possibilities in mind without committing to any particular one. Others find ambiguity stressful, strongly preferring to reach conclusions even when evidence doesn't clearly favour any particular answer. These different emotional responses to uncertainty affect how people engage with cases like Atlas. Scientists, being human, aren't immune to these emotional dimensions. A researcher who finds the possibility of alien artifacts exciting might unconsciously give more weight to observations that support that interpretation. One who finds the idea implausible might unconsciously emphasize alternative explanations. These biases don't necessarily invalidate conclusions, but they're worth recognizing and, when possible, compensating for. The media coverage of Atlas illustrated how emotions can shape public discourse. Some outlets emphasized the mystery and possibility of artificial origins, playing to readers' sense of wonder and curiosity. Others took a more skeptical tone, framing artificial explanations as fringe ideas not to be taken seriously. These different framings weren't just about the science, they reflected judgments about what emotional tone was appropriate and what audience reactions were desirable. Public reactions to the Atlas case similarly showed the emotional dimensions. Online discussions revealed people who were excited by the possibilities, eagerly interpreting each new observation as potential evidence of artificial origins. Others were skeptical or even dismissive, arguing that hoping for aliens was wishful thinking not supported by evidence. These reactions went beyond rational evaluation of data to include hopes, fears, and preferences about what people wanted to be true. Recognizing these emotional dimensions doesn't mean dismissing them as irrelevant. Emotions are part of being human, and they provide important motivation for scientific endeavours. The wonder and curiosity that drive people to study the universe are emotional responses. The excitement of potential discovery energizes research and attracts talented people to the field. But it does mean being aware of how emotions can influence reasoning. When we find ourselves strongly hoping for or against a particular conclusion, that's a sign to be especially careful about evaluating evidence. Am I seeing what's actually there, or what I want to see? Am I dismissing possibilities because they make me uncomfortable? Am I accepting ideas because they're exciting even if they're not well supported? These questions don't have easy answers, and perfect objectivity is probably impossible. But asking them, being reflective about our own reasoning processes and the emotions that might influence them, is part of thinking carefully and honestly about complex questions. The Atlas case, with its ambiguous evidence and extraordinary implications, has been a kind of emotional Rorschach test. People's reactions to it reveal their hopes and fears, their tolerance for uncertainty, their willingness to consider unconventional ideas. Some see exciting possibilities, others see cautionary tales about jumping to conclusions. Both responses are understandable and reflect genuine aspects of the situation. Perhaps the healthiest emotional response is to allow ourselves to feel wonder at the questions while maintaining appropriate skepticism about answers. We can be excited by the possibility of discovering alien artifacts while recognizing that most unusual phenomena have natural explanations. We can take anomalies seriously without assuming they must indicate technology. We can remain open to surprises while demanding rigorous evidence before accepting extraordinary conclusions. This balanced emotional stance, like balanced intellectual stance, is difficult to maintain. But it's worth striving for. It allows us to engage fully with the wonder and importance of questions about life in the universe while thinking clearly about evidence and arguments. It enables us to be emotionally invested in the search without letting those emotions overwhelm our judgment. As our journey through Atlas's story nears its end, it's worth contemplating what the future might hold for this young field of interstellar object research. The next decade will likely bring transformative progress, with new discoveries and capabilities that will reshape our understanding. The Vera Rubin Observatory, scheduled to begin full operation soon, will be a game-changer for detecting interstellar objects. Its wide field of view and sensitive detectors will allow it to monitor vast swathes of sky repeatedly, catching faint moving objects that previous surveys would have missed. Within a few years of operation, it should detect dozens of interstellar visitors, building up a catalogue large enough for meaningful statistical analysis. With larger samples, we'll be able to address questions that are currently unanswerable. What fraction of interstellar objects are icy comets versus rocky asteroids? Do they show compositional differences that might indicate diverse stellar origins? Are unusual objects like Oumuamua and Atlas rare outliers or representatives of a common population we haven't adequately sampled? The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will complement ground-based surveys with observations from space. Free from atmospheric interference and capable of infrared observations, it might detect interstellar objects by their thermal emission, rather than reflected light, potentially finding very dark objects that optical surveys would miss. Advances in spectroscopic techniques will enable more detailed characterization of future interstellar visitors. New instruments can measure isotope ratios more precisely, constrain composition better, and detect fainter spectral features. Each technical improvement adds information that helps discriminate between different hypotheses about origins and nature. Spacecraft missions to intercept interstellar objects, while still challenging and expensive, are becoming more feasible. Conceptual studies are being conducted for various mission architectures. If an object on a particularly favourable trajectory were detected early enough, and if sufficient funding and political will could be marshalled, a mission could potentially be launched within a decade of detection. Such a mission would transform interstellar object science. Close-up imaging would reveal surface features invisible from Earth. Direct sampling could analyse composition precisely. Instruments could search for any artificial signatures that might exist at levels too subtle for remote detection. Even if all interstellar objects turn out to be natural, the scientific return from such a mission would justify the investment. Beyond these near-term developments, we can imagine longer-term possibilities. Future generations might have telescopes powerful enough to detect interstellar objects while they're still far outside the solar system, years before close approach. This would provide unprecedented time for observation and planning. Eventually, we might even develop the capability to deflect interesting objects slightly, altering their trajectories to pass even closer to Earth for better study. Looking further ahead, perhaps centuries or millennia rather than decades, humanity might send its own probes beyond the solar system. These probes would eventually become interstellar objects themselves, carrying messages from Earth into the cosmic ocean, much like the Voyager spacecraft with their golden records. If another civilization ever encounters these probes, they might face the same questions we're facing about Atlas. Is this object natural or artificial? What can we learn from it? This symmetry is thought-provoking. We're attempting to recognize alien artifacts in our solar system, while simultaneously creating artifacts that will one day be alien to other systems. Both activities express the same fundamental drive: curiosity about what lies beyond, desire to explore and understand, hope for connection across the vast spaces that separate intelligent beings. The scientific and technological progress described here is likely but not guaranteed. Funding must be allocated, telescopes must be built, missions must be approved and successfully executed. There will be setbacks and surprises, plans that fail, and unanticipated opportunities. But the overall trajectory seems clear. We're going to learn much more about interstellar objects in the coming years than we currently know. This progress will occur whether or not Atlas was artificial. If it was natural, studying it and other interstellar objects will teach us about the diversity of small bodies throughout the galaxy, about the processes that eject them from their home systems, and about the conditions in stellar systems beyond our own. If it was artificial, that discovery would be even more momentous, opening entire new fields of study and transforming our understanding of life in the universe. Either way, we're living through the early stages of a new era in astronomy. Future generations will look back on this time as the beginning, when we first started detecting and studying visitors from beyond our solar system. The questions we're asking now and the methods we're developing to investigate them will shape this field for decades to come. In these final reflections, there's something worth saying about mystery itself and its value in our lives and in science. Atlas, by remaining ambiguous, by not clearly revealing whether it's natural or artificial, offers a particular kind of gift. The gift of genuine mystery, of questions without easy answers. Our modern world often seems to have lost its mysteries. We have explanations for how things work, maps of every land, encyclopedic knowledge available at our fingertips. The unknown has retreated to the frontiers of science, to quantum mechanics and consciousness, and the deep past and distant cosmos. Mysteries still exist, but they require sophisticated instruments and advanced mathematics to even encounter. Atlas represents a different kind of mystery, one accessible to anyone who cares to contemplate it. We observed this object, we measured its properties, we analysed its behaviour, and we still can't definitively say what it was. The mystery isn't about lacking data. It's about data that doesn't cleanly fit our categories, that allows multiple interpretations, that resists simple explanation. This kind of ambiguity can be uncomfortable, but it's also valuable. It reminds us that the universe doesn't always conform to our expectations or fit neatly into our conceptual boxes. It teaches humility about the limits of current knowledge. It encourages imagination, inviting us to think creatively about possibilities we might otherwise dismiss. Mysteries also create space for wonder, for that feeling of awe and fascination that comes from encountering something that surpasses our understanding. This wonder is one of the deepest pleasures available to thinking beings, a sense of connection to something larger than ourselves, appreciation for the complexity and strangeness of existence. Science sometimes seems to eliminate wonder by explaining away mystery. When we understand how rainbows form or why planets orbit as they do, have we lost something precious by replacing magical ignorance with mechanical knowledge? Some romantics argue yes, claiming that scientific explanation diminishes beauty and wonder. But Atlas shows that science can create new mysteries even while solving old ones. By developing the capability to detect interstellar objects, we've opened access to phenomena that previous generations couldn't even observe. These phenomena raise new questions, reveal new complexities, show that the universe is stranger and more diverse than we'd imagined. Science, far from eliminating mystery, continually reveals new depths of mystery in previously unknown or unexaminable phenomena. The specific mystery of ATLAS, whether it was natural or artificial, matters less than what the mystery teaches us. It shows that we're still explorers, still encountering phenomena we don't fully understand. It reminds us that there are questions we can ask but not yet answer, observations we can make but not yet interpret definitively. This is the human condition at its best, curious, uncertain, reaching beyond current knowledge toward deeper understanding. There's also something valuable about mysteries that unite people rather than dividing them. Different researchers studying Atlas reached different conclusions, but they were all investigating the same question, examining the same evidence, participating in the same discourse. The mystery created common ground for discussion, a shared sense that something interesting was happening even if people disagreed about exactly what it meant. In a world often divided by certainties, by people convinced they have the right answers, and those who disagree are simply wrong, mysteries offer neutral territory. We can disagree about interpretations while agreeing that the phenomenon itself is interesting and worth studying. We can hold different hypotheses while respecting those who hold alternatives. The uncertainty creates space for civility and productive dialogue. This doesn't mean all opinions are equally valid, or that we should never reach conclusions. Evidence matters, and some interpretations fit data better than others. But when evidence is genuinely ambiguous, recognizing that ambiguity and embracing the resulting mystery is more honest than pretending to certainties we don't possess. The mystery of ATLAS, whether eventually resolved or remaining perpetually ambiguous, has already enriched our understanding. It's pushed researchers to think more carefully about what would constitute convincing evidence of artificial objects. It stimulated development of better observation techniques and theoretical frameworks. It's engaged public imagination and drawn attention to the emerging field of interstellar object studies. These contributions would be valuable even if we eventually determine with certainty that Atlas was an ordinary comet, unusual but entirely natural. The path of inquiry matters, not just the destination. The questions we ask and the methods we develop for investigating them are themselves achievements, regardless of what specific answers we eventually find. So perhaps we should thank ATLAS, this mysterious visitor from beyond, for the questions it raised and the wonder it inspired. Whether natural or artificial, whether understood or forever ambiguous, it's given us the gift of genuine mystery in an age when mysteries are precious and rare. Thank you for staying with me through this long journey through the mysteries of ATLAS and the questions it raised about our place in the universe. We've travelled together through 2.5 hours, exploring the observations that made this object so unusual, the debates about what those observations might mean, and the deeper questions about how we search for and recognise evidence of intelligence beyond Earth. We've journeyed from the initial detection of a faint object in the September 2019 skies, through the accumulating anomalies in its behaviour and fragmentation, to the debates about whether natural or artificial explanations better fit the evidence. We've contemplated the statistics of interstellar visitors, the psychology of scientists grappling with ambiguous data, and the philosophical implications of potentially encountering technology from another civilization. So what about that question we began with? What is the disturbing reason scientists think Atlas might be artificial? The answer, as honestly as I can give it, is not a single definitive piece of evidence, but rather an accumulation of subtle anomalies, each individually explainable but collectively forming a pattern that some researchers found difficult to dismiss entirely. The regular fragmentation, the unusual acceleration profile, the thermal peculiarities, the coordinated behaviour of multiple fragments, altogether created a picture that didn't quite match expectations for natural objects. But it's crucial to emphasize that this doesn't mean Atlas was definitely artificial. Most scientists who studied it favored natural explanations, and those explanations, while requiring some special assumptions, remain viable. The disturbing aspect isn't that the evidence clearly points to artificial origins. It's that the evidence is ambiguous enough that the question can't be dismissed outright, that reasonable researchers examining the same data can reach different conclusions. If you enjoyed this thoughtful exploration of cosmic mysteries and the challenges of interpreting ambiguous evidence, a like would help others find these calm investigations of the universe's puzzles. And please share your thoughts in the comments. How do you think about cases like Atlas, where evidence permits multiple interpretations? What would you accept as convincing proof of artificial origins? Where in the world are you, and what draws you to these questions about life beyond Earth? Wherever you are in the world, whatever time you're experiencing this, I hope your breathing has slowed into gentle rhythms. I hope the day's worries have faded into the background. I hope your mind has found some peace in contemplating these distant questions, these cosmic mysteries that put our everyday concerns in perspective. I hope your body has settled into complete comfort, ready for deep and restful sleep. Look up at the stars tonight if you can, or picture them in your mind if you cannot. Out there, beyond the visible stars, beyond our solar system's familiar planets, interstellar space is filled with wandering objects. Most are undoubtedly natural, comets and asteroids ejected from their home systems, drifting through the galaxy for millions or billions of years. But perhaps, just perhaps, some are more than natural. Perhaps some carry within them evidence of intelligence, artifacts from civilizations that arose around distant suns. Remnants of exploration, or exploitation, or simply of existence. We may never know for certain about Atlas. The object and its fragments have faded from view, continuing their journeys beyond our ability to observe. But the questions it raised remain, and they're questions that matter. They push us to think carefully about what we would accept as evidence of extraterrestrial intelligence. They remind us that the universe might hold surprises we haven't imagined. They keep alive the possibility of wonder, even in an age of advancing knowledge. The scenario that keeps scientists awake about ATLAS isn't a nightmare of alien invasion or cosmic danger. It's the gentler but still profound uncertainty about whether we've already encountered evidence of intelligence beyond Earth and simply couldn't tell for certain. It's the awareness that our methods for detecting and recognizing alien artifacts might not be adequate, that we might miss or misidentify the very things we're hoping to find. It's the humbling recognition that the universe's secrets don't yield easily to our investigations. But there's beauty in this uncertainty, in the questions that remain open, in the mysteries that persist despite our best efforts to solve them. Atlas, whether natural or artificial, whether understood or forever ambiguous, has enriched our journey of discovery. It's shown us that we're still at the beginning, still learning how to ask the right questions and interpret the answers the universe provides. Sleep well. Dream of objects drifting through the dark between stars, carrying stories we may never fully know. Dream of the slow, patient work of observation and analysis, of scientists carefully weighing evidence and building understanding piece by piece. Dream of the questions that await us as we continue exploring the cosmos, the discoveries not yet made, the mysteries not yet encountered. Good night. May your rest be deep and peaceful. May your dreams be filled with wonder at the vastness and strangeness of the universe, and may you wake tomorrow with renewed curiosity about the cosmos and our place within it. Good night.